So far, we've talked quite a bit about individual convergence tests that you could use to determine whether or not a series converges to a finite number or doesn't. And today we're going to try and focus on determining which one of those tests is the best one to use in a given scenario. And so overall, the idea is always going to be that we're going to want to compare a complicated series to one that we already know. And typically that means either a geometric series or a series where you could use the p-test. And so as a quick review up here, a geometric series is any series of the form a times r to the n. And so in other words, between the terms, you're multiplying by that constant r. Or the p-test corresponds to series of the form 1 over n to the p. And for a geometric series, we know that this will converge as long as the absolute value of r is less than 1. And for the p-test sort of series, we know that this converges if p is greater than 1. And in both cases, if the other sort of condition is met, so if r is greater than or equal to 1, or if p is less than or equal to 1, then the series will diverge. Okay, so when we're trying to analyze more arbitrary series, we're going to want to keep in mind the sort of growth rate of different functions. And so the thing to know is that logarithms are typically slower than polynomials, which are slower than exponentials, which are slower than factorials. And so to make this a little bit more explicit, what I mean is that something of the form the natural log of n is always going to be slower growing than something of the form n to the c, where c is any constant, so n squared, n cubed, whatever. And that's always going to be slower than something of the form r to the n, where here I'm assuming that r is greater than 1. And that's always going to be slower than something like n factorial. And so factorials are going to come up over the next few days. And as a reminder, hopefully you've seen this before. If not, that's okay too, though. This represents the product of n times n minus 1 times n minus 2 down until we get to 1. And so, for example, 3 factorial just stands for 3 times 2 times 1, or in other words, 6 in this case. Okay, let's see how these rules apply to a couple examples. And so my goal for today is to run through all of the possible tests that we've seen so far and check whether or not each one would be appropriate to analyze a particular sum. And that way we can get some more intuition about when each test is good or bad for a particular problem. And so for this sum right here, where we have 1 over 2 to the n minus root n, the idea overall is that we want to look for the biggest term in the numerator and the biggest term in the denominator. In the numerator, there's only one term, that's the 1. In the denominator, there's an exponential and a polynomial. And so this isn't really a polynomial strictly speaking, but it's an n to the 1/2. Right? And so that corresponds to this case right here. And so I know that the n to the 1/2 is much smaller than a 2 to the n, which is exponential. And so my intuition should be that overall this series is approximately like 1 over 2 to the n. And I know that that converges because it's going to 0 exponentially fast, or in other words, it converges because it's geometric. And so now I have to find a way of justifying that this converges because it's roughly geometric by using something more precise. And so in other words, I want to find exact tests that will verify this intuition is correct. And so let's run through the tests that we have and see whether or not each one would be useful or not in this case. And so the nth term test, that's that test that says you take the limit of the individual terms, and if it's not 0, then the series diverges. In this case, this isn't helpful, and the reason is because the terms go to 0. Right, so in other words, if I take the limit of 1 over 2 to the n minus root n, that's 0, and so the nth term test just doesn't help. It doesn't tell you anything. So now we could check the direct comparison test. And so that would be asking, is there something that's less than or greater than this expression right here that would be helpful to use a comparison for? And this is a little bit iffy here. And the reason is that we have a minus sign in between the terms. And we want to show overall that this series converges. And so ideally, we'd like to be able to say something like this is less than 1 over 2 to the n. But it's not less than that because we're subtracting in the denominator, which makes the whole thing bigger. And so this is probably not. I'll say it's sort of iffy. And the reason for this is because there's a negative in the denominator, which doesn't help. And so if this had been a plus instead, then we could have said that this was less than or equal to 1 over 2 to the n, and then we would have been good to go. It turns out that maybe you could do something more complicated with the direct comparison test that would work here, but I'm not really going to worry about that for now. Because the next test, the limit comparison test, will be useful. And the reason that this is useful is because there are clear leading terms here that we can analyze. And so by the leading terms, I mean the biggest thing in the numerator and the denominator. And so that would be the 1 and the 2 to the n. So the 1 in the numerator and the 2 to the n in the denominator that are easy to analyze. Okay, and then the last thing, just to check the test, even though we already know that we have a good one to use, I just want to see what would happen with the other ones. And so the integral test, this would need to be a positive, decreasing, continuous function that was easy to integrate. And the point is that 1 over 2 to the x minus root x is not easy to integrate. And so this is not going to be a good choice here. And so it is the case that the integral test theoretically might apply. It's just not going to be useful because I don't want to do the integral of 1 over 2 to the x minus root x. That's not going to help. Okay, so at this point we've concluded that this limit comparison test is probably the best option for this series. And so that means that we're going to want to let b sub n be the corresponding sequence that's just the leading terms of my original sequence. And so in this case, that again is that 1 over 2 to the n. And then we'll take the limit of the ratio, so the limit as n goes to infinity of the original thing, so that's 1 over 2 to the n minus root n, times, and then in this case, the reciprocal of the b to the n, which is really the same as dividing by b to the n. And so in this case, that'll just be the same as multiplying by 2 to the n. And so now I'll rewrite this as a one fraction, so that's 2 to the n over 2 to the n minus root n. The easiest way to deal with these often is to divide by the largest thing you can see anywhere in the expression. And so that would be the 2 to the n here. And so I'm going to divide the numerator and the denominator all by 2 to the n. And so on the top I just get 1. In the bottom I get 1 minus root n over 2 to the n. And here is where I'm going to use that intuition that polynomials are slower than exponentials. And so I just know that this term here has to go to 0 because the exponential dominates. And so once I have that, then I know that this limit is equal to 1. And so by the limit comparison test, because this value is between 0 and infinity, that means that the series 1 over 2 to the n minus root n does the same as the series 1 over 2 to the n by the limit comparison test. And also, we know that 1 over 2 to the n converges because it's geometric. And in this case, r is equal to 1/2, which is less than 1. And so the overall conclusion then is that the original series converges. Okay, so now let's look at the next problem, where again we're going to want to check and see which one of these tests will be the most appropriate to analyze the sum from n equals 1 to infinity of e to the n times n to the minus 3/2. So again here I want to think about what is the biggest term here overall. And first of all, this doesn't really have multiple terms here because we're multiplying things together. And so when we talk about leading terms, that's generally what we consider when there's pluses in between. And we want to figure out which term is the biggest out of the pluses. But here, everything's sort of multiplied together, so all of this is just the leading term. And so I still need to figure out what's happening with the exponential versus the n to the minus 3/2. And what we already have seen is that exponentials always grow faster than polynomials. And so overall, that means that e to the n times n to the minus 3.2 explodes. as n goes to infinity, because that exponential dominates. And so that's just talking about the sequence, not the series. And if the individual terms are exploding, then certainly that means that the series will diverge as well, because we're adding bigger and bigger numbers together. And so this means that in this case, the nth term test is helpful. And that's because the terms explode themselves. And if they explode, another way of saying that is that they don't go to zero. All right, so as soon as we see the nth term test applies, that's almost always the easiest test to apply. And so none of these are going to be good to use, and that's just because the nth term test already worked. And so the nth term test is sort of a sanity check for, is it obvious that the series diverges? And so that's always something that you want to think about first. And there's no reason to consider the other tests if the nth term test worked. And so the sort of formal solution here would be to say that the limit as n goes to infinity of e to the n times n to the minus 3.2 is equal to infinity because exponentials dominate over polynomials. If I wanted to be a little more formal, I could probably do something with L'Hopital's rule, but I'm not going to worry about that here. And so with this reasoning, that means that by the nth term test, the series diverges. All right, so in a minute, we'll look at some other examples where they're very close to these series, but you might want to use other tests.